Hello, my name is Benjamin Canton, and I am a senior at the University of Massachusetts Amherst. I study mechanical engineering and am also a member of UMass's Integrated Concentration Science program. Today, I'll be talking about the impact of ocean swells on floating offshore wind turbines. I'll be focusing specifically on the effects of wave periods and wind-wave misalignment. So why is offshore wind important? As the effects of climate change have become more pronounced, countries are switching to cleaner, more sustainable sources of energy, one of which is offshore wind. While the United States is the leader in land-based wind energy, the country lags far behind European countries when it comes to offshore wind. Compared to land-based wind, offshore wind is faster and more consistent. The National Renewable Energy Laboratory has estimated that offshore wind can provide up to 4 times the country's current electric capacity. This is especially important considering how much of the U.S. population lives in coastal areas. Offshore wind farms will provide an easy access to clean energy for high-density urban areas along the coast, where electricity is expensive and land is scarce, making it difficult to build additional land-based energy infrastructure. Most commercial offshore wind farms in the world are in shallower water and involve a substructure that is attached to the seafloor, for example a monopile or a jacket. Alternatively, floating wind turbines allow wind farms to be built in locations with deeper water where fixed-bottom wind turbines would be too expensive. An example of such a location would be off the western coast of the United States, where the continental shelf is much narrower and there is not a lot of shallow water to build fixed-bottom wind farms. Although there are a few different floating platform designs, in my research I'll be focusing on floating turbines with semi-submersible platforms, such as the one shown in this picture. In this configuration, the platform is floating on a body of water, and mooring lines are anchored into the seafloor to keep the platform from drifting too far off. However, the combination of a floating platform and more extreme ocean conditions found in deeper water means the turbine is much more susceptible to ocean waves. The most common type of wave found in the ocean is surface gravity waves. There are 2 kinds of surface gravity waves: wind-sea waves and swell waves. In the case of wind-sea waves, the wind transfers momentum to the water, causing waves to form. These waves travel in the same direction as the wind and stay within a smaller area. Swell waves are slightly different. They start out as wind-sea waves, but they are usually formed during storms such as hurricanes and monsoons. In storms, the winds are usually stronger, which means larger waves. Eventually, these waves will leave the storm area. Once they leave, they are no longer coupled to a local wind field and become known as swells. Swells have longer periods, higher wave heights, propagate long distances, and can travel in directions different from the wind. Swell waves also dominate the sea state, especially near the equator where storms are common. Many offshore wind turbine studies have looked at turbine and platform motion and loading from wind-sea waves that are aligned with the wind. There is less research on how floating turbines are impacted by swell waves, especially waves that are misaligned with the wind. I will be focusing on how swell waves affect turbine and platform behavior, particularly with respect to wave direction and wave period. In my research, I used the wind turbine simulation program OpenFast, developed by the National Renewable Energy Laboratory, to simulate a wind turbine mounted on a floating semi-submersible platform. Aerodynamic forces from the wind and hydrodynamic forces from the waves apply loads on the turbine and platform, causing them to move. The turbine was simulated using 2 different cases to see if there was a noticeable difference in the platform motions, one with a wave period of 10 seconds and 20 seconds in the other. These periods correspond to the high ends of wind, sea, and swell waves in the ocean. In both cases, the wave height was set to 3 meters in order to isolate the effects of changing the period. The wave profile on the ocean surface was modeled using this equation, where nu is the wave elevation at a given horizontal position x and time t. H, L, and t are all constants corresponding to wave height, wavelength, and wave period respectively. This equation comes from linear wave theory, which is a quick but accurate enough approximation of wave propagation compared to higher-order nonlinear methods that can be computationally expensive. The resulting profile is a single sinusoidal wave. Realistically, at any given time, the ocean surface is highly irregular and consists of many waves, all with different amplitudes, periods, phases, and directions. This picture is a visualization of what the simulation is doing. Here we have a semi-submersible platform in red, with the tower mounted on top. The platform is floating in a wave field, with the black representing the highest wave elevation and the white representing the lowest wave elevations. Alright, Now that we've seen an image of the turbine and platform under wind and wave loads, what exactly are we looking for? As seen in this picture, the platform is able to move in 6 separate directions. It can move linearly along the X, Y, and Z axes, which are called surge, sway, and heave respectively. The platform can also rotate about these axes. These rotations are called the roll, pitch, and yaw, again corresponding to the X, Y, and Z axes. Additionally, the force of the wind acting on the turbine blades causes the tower to experience bending moments about its base. The waves were also misaligned at 15, 30, 45, and 60-degree angles to see what effect wind-wave misalignment had on the platform. The turbine was simulated for a half hour, and the platform displacements, tower moments, and fair lead and anchor tensions were all recorded over time. Here, we use platform surge and tower base bending moment versus wind-wave misalignment as examples of the simulation results. These plots are summary statistics in the form of box plots. The physical response is sinusoidal, so in these box plots, the red line represents the median, and the minimums and the maximums can be used to find the amplitude of the response. The median surge was the same for both the 10-second and 20-second period waves. However, longer period waves caused greater displacement in the platform. This trend is seen throughout many of the output variables that were looked at, suggesting that longer period swell waves may cause larger displacements than waves with smaller periods, even if the amplitudes are the same. Furthermore, as the wind-wave misalignment increases up to 60 degrees, the surge decreases since the waves are no longer moving along the x-axis. For tower bending moments, the moment does not seem to change with the wave period. However, wave direction does have a big impact. When the waves are in the same direction as the wind and moving towards the rotor, there is very little bending moment. The rotor acts as a damper in this case. When the waves are misaligned up to 60 degrees, they are no longer facing the rotor head-on, allowing for greater bending moments. The results of the simulation show that the different wave periods, such as those seen in the wind, sea, and swell waves, do play a role in turbine and floating platform motion. Longer periods can cause greater displacements, and wind-wave misalignment can cause greater bending moments. Both of these characteristics are common in swell waves, and along with their higher amplitude, swells have the potential to cause greater loads on offshore turbines. Understanding the effects of swell waves on offshore wind turbines will be increasingly important as floating wind turbine technology improves and wind farms are built in deeper water. Thank you for watching this presentation, and I hope you enjoyed it. I would like to thank Professor Matthew Lackner for all of his help throughout the research process and for improving my understanding of hydrodynamics, wind turbines, and the OpenFast code. I would also like to thank Professor Scott Auerbach and my peers in the US ICONS program for their guidance and feedback.